Which one they work? So which one they work? Groundwater.
Underground water.
No, groundwater, yes. Or we're going to use what we call long distance water supply.
What?
You see my screen?
Yeah. Yes.
Good.
Yes.
Then there's another thing. You need to check out for environmental influences, what we call anthropogenic influences. In other words, what is the human activity within this vicinity is important. In ideal case, if you are using groundwater, for instance, you should be able to locate your groundwater in a location where your water will not be contaminated.
Yes.
That means it must be free from agricultural activity. There must be a buffer zone. It must be free from mining activities. It must be free from any activity that will reduce the quality or quantity or extraction ease of the water. I've mentioned three things: the quality, the quantity.
Yes.
We call it the economics. Let me use the word the economics.
The economic what?
Economics of extraction.
Okay.
In other words, the quality must be assured. You know what I mean? The quality must not be affected. The quantity must not be affected. And then the ease, the economics of extraction must be easy, must be simple. Or better put, the energy of extraction must be minimal. The reason is this: if you put your water in a place where, let's say you're coming from where? Hello? You say where do you stay?
I stay in Lagos.
Okay, Lagos. Okay, don't worry.
Mainland.
Let's say you are in Lagos now, and you decide to use the water from the lagoon. You know that's impossible. That's near impossible.
That's surface water.
That's surface water. You might not be able to use it because Lagos Lagoon is not in the best shapes. Okay. Even if you decide to use a water around, I'm not too conversant with Lagos, but let's say where there are oil mining activities, oil extraction activities.
Like Port Harcourt?
Like Bayelsa, Port Harcourt. Then you must be careful because at the end of the day, the groundwater itself is contaminated with iron. So you must describe your area very well. I'm telling you the materials now. That's the first start.
I've seen the content.
Okay. That's the first start. There's a lot of material I'm going to be sending you, but I'm going to do it bit by bit.
It's okay.
It's a whole lot. Meanwhile, I also refer you to the website where you download the software when it's time for that.
It's okay.
Good. So let's go back to our introduction. We are still in introduction.
It's okay. Mapping and topography.
Mapping and topography. We are done with that. Then you describe the area. So the next one is
description.
Description. No, we've done description now. That was what I'm telling you. Description, you must ensure three parameters. Quality, you must ensure sustainability of quality, sustainability of quantity,
and economic of extraction
or availability. You can subtract that one for availability.
It's okay.
Okay. So
availability of the water.
Yes. Availability cum sustainability. It's just gone. So the next thing you do now is description of calculation basis. Now, what do we mean by this? Who are you designing for? Is it for industrial area? Is it for residential area? You need to know. If it is for
commercial,
if it's for commercial, residential, commercial, or industrial, or agricultural, the
yes.
inexhaustive. Okay. The list is
like
industry
irrigation.
or for hybrid. It can also be for a hybrid area. Now, why do you need that calculation basis? This is because every user has different water demand. If you are talking for residential, it is it's very simple. You can say, what is the standard water demand per person per day? What quantity of water am I assigning to residential people? That one is as simple as ABCD. In international standard, it is between 100 and 150. The quantity of water required per person per day. Are you with me?
Yes,
It
I'm
varies
with you.
between the World Bank WHO standard is 150. In Nigeria, we use between 60 to 100.
It's okay.
Abuja was designed with 100.
So any location in Abuja, you use that calculation basis?
God bless you. If it's a local area, you adapt.
What about Lagos? Sorry, what about Lagos?
Lagos will use 100 also because the standard of life in Lagos and Abuja is not different.
It's okay.
Good. Then if it is industry, you ask yourself, what is this industry producing? In those materials I send you, there are standards there already. If you are producing a brewing industry, then you ask yourself, what is their output a day?
That's brewery and beverages. Are they on the same category?
Yeah, they are there.
Breweries and beverages.
Yes, you need to use their output, their production output. If it is water they are using, you put their production output. If the workers are living there, you now assume residential parameters for them. If they have agricultural land and they are producing, depending on the kind of crop they are producing, you assigned water demand per crop. If it's a place they are producing pure water, you ask yourself, the pure water industry, what is their output demand? What is their likely output demand per day? So you see, these things are not cast on stone. But the good thing is that there is a standard, there's a chart that describes every field, what you need. Okay? Let me digress a little bit. Let me open one of these materials. Lecture materials. I've sent you this. Let me open this. Okay. This is chapter 2. They have 8 chapters. So let me just show you an example of what I'm talking about. For instance, okay, not in this one. Okay, I'm opening the wrong chapter, sorry. Chapter 1, introduction. So, you know, in design, if you're doing a design, it's not something you do on hand. You must need charts. You must need tables. Okay. Yes. For instance, now, this is like example now. Just to give you an idea. Are you seeing my screen?
Yes.
Good. Drinking water, for instance, is 3 to 10 liters per person per day. These are all standards, and I'll give you those standards. You have those standards, okay?
What was the ICP? The unit?
Okay, the unit is liters per capita per day.
It's okay.
Liters, LCD, liters per capita per day.
Yes.
Even if somebody says, listen to me, if somebody says liters per hectare, your mind should tell you it's talking about irrigation.
It's okay.
Per hectare. Now, there's what we call land use. If you are designing for a place where there are no houses, okay, you're going to make use of what they call land use. And land use will tell you how many people per hectare. Low density, medium density, high density. It depends. Let not digress too much. I'll still come to that. Now, look at this now. You can see what you need in a day. Car washing, irrigation, flushing of toilets, washing of clothes, and everything. These are just their range. But at the end of the day, we expected to have between 100 and 150 water demand per person.
Sorry, I have the unit is expressed in liter per capita daily day.
Yes.
Why is it not liters per volume?
Now, thank you so much. That's a good question. Very good question. Now, for you to convert it to liter per person per day, it means you need to multiply with number of persons, what you call population equivalent. Are you with me?
Yes, I'm with you.
Once you multiply, let's say in your room now, if you now want to calculate how many people, if you now want to convert it to liters per seconds or meter cube per seconds, okay, you multiply by population equivalent. That's all.
It's okay.
This thing is like giving you what we call specific value. You know those days we have specific latent heat, specific value. So if you now want to convert specific value to a usable value, you now multiply by the units.
It's okay.
For instance, let me just give you a layman's example now. Let me get whiteboard. Let me share a whiteboard, for instance.
It's okay.
Okay, this is a whiteboard. Just hold on, listen to me. For instance, I'm assigning 100. Or should I use tests? Okay, good.
Yes.
I'm assigning 100.
Yes.
Liters per capita per day. And there are 10 people in your house, in your room now. Let me tell you the demand now. So there are 10 people. These 10 people, this 100, the unit is in liters per capita per day. Then multiply by 10 capita.
Yeah, people.
God bless you. You know, in engineer we say, in what I would say capita. Capita.
It's okay.
Now, if you multiply this,
1,000.
God bless you. So it will give us 1,000. I'm assuming you guys will consume, each person in your house is consuming 100, okay?
It give you 1,000 liter per capita square.
No more capita square again. No, you're wrong, sir. Capita is denominator, the other capita is numerator.
It's okay, per day.
It will not give you 1,000 liters per day. Now, one day is the equivalent of
24.
60, okay. 24
seconds
times 60 times 60. That will give you A6400.
Seconds. What unit?
Seconds.
Seconds. It's okay.
You know, 24 is hour. 60 is minutes. And this is it's the same thing.
No.
It's the same thing. It's seconds, into seconds, Now, liters. When we say liters, 1,000 liters is equal to 1 cubic meter.
1 meter cube.
Yes. So at the end of the day, you can convert this into meter cube per second, which is what you want, which becomes your Q, which becomes your flow, okay? Q can come in different units. It can come in liters per seconds or meter cube per seconds, or it can come in different units, or it can also come in meter cube per day. Look, listen, do you know why we aggregate them? If the number of zeros are becoming too much,
you divide by 1,000 now to be meter cube per seconds.
Good. So all of them
and you leave it in day.
Yes.
You don't need to multiply.
God bless you. Now let me just give you one thing. This thing in modeling, we call it discretization.
What?
In modeling, we call it discretization.
It's okay. Discrete. It's okay.
Discrete, yeah. Now, if you are looking at big unit, let's say if you are talking about wastewater treatment plants, what they will ask you if you are designing wastewater treatment plant, they will ask you what is the flow per day. They won't be asking you per second, because their unit of treatment is in day. You know, they have a primary sedimentation tank, so it's holding pound per day.
And it operates for 24 hours.
God bless you.
Our day in, day out.
God bless you.
Just for maintenance period.
Yeah, that's right. But if you're talking about water reticulation, you'll be dealing in the smallest units. And that will be liters per second.
It's okay.
You'll be dealing on the smallest units.
If you are talking about what?
Water reticulation, water distribution.
It's okay.
Water distribution, you'll be talking about liter per second.
Water distribution.
You'll be talking about the lowest, the smallest units. You know why? You know why so?
Distribution. Maybe
it's so because water is required per second.
Is
required every second. Water is required.
Yes.
Because you don't know when somebody will be thirsty. You don't know when they will be floating. You don't know when they will be cooking. You don't know when they will be bathing. So water coming to your house is not something that comes once in a day. It's something that there's always is a real time thing. Okay. Now everything about water reticulation, Femi, is simply to design your pipe sizing. In the water reticulation, your major aim is to design your pipe. That is the
design the pipe.
That's the major thing.
It's okay.
Because designing the pump is not difficult. Just what is the head difference? What is the pipe length? And then what is the frictional coefficient of the pipe? Give me those three values. I will tell you the pump you need. What is the vertical head loss?
The horsepower.
Yes. What is the vertical head loss? What is the what is the horizontal head loss? Okay.
It's okay.
If you add the two, and then of course, what is the internal head loss in the pump? With those three, you design the pump. So designing the pump is not a difficult thing. But our emphasis, our aim, is to design the pipe network, because it is the pipe that conveys the water.
Yes.
If the pipe is too big, problem. If it is too small, problem. The pipe.
What about the thickness? What about the thickness of the pipe?
The thickness of the pipe is a function of pressure.
Yes.
And a function of pressure is a function of height.
Yes.
So if you know the height, it will tell you whether it's 8 bar, 6 bar, or 10 bar. But as a standard in Nigeria or in Germany, which also relates to Nigeria, the minimum bar, pressure of a pipe or cum thickness is the one that will resist 8 bars. I repeat, you can write that one down. 8 bars. The minimum pressure. No, not the minimum, so pardon me. The maximum.
Maximum?
Yes.
Maximum pressure?
Required in a network. It's 8 bars.
8 bar?
Yes, 8 bars. In other words, if you are designing your water network, the pressure, the anticipated pressure in the network must not be more than 8 bars.
It's okay.
So if you go to the market to buy a pipe, for instance, you will look at the body of the pipe. It is written there, 6 bars, 8 bars. It starts from 4 bars. Okay. These ones that we use, this green one that we use for plumbing, house plumbing, you know, it's 4 bars.
Yes.
So there's a one for 8 bars, but that one is more expensive. That one is.
What about the one they use in distributing water? Maybe from water treatment plants.
That one is usually around 10 bar, depending on the height difference between the treatment plant and the consumers.
It's okay.
You understand the point now?
Yes.
But in ideal case, it should be within minimum of 8 bars. You know why? Because The pressure in the network must be less than 8 bars. So you
It's okay.
that is bringing the water must be minimum of 8 bars.
It's okay.
Good. So these 8 bars, let me give you an idea. These 8 bars is equivalent to 80 meters. These 8 bars is equivalent to 80 meters.
Okay.
You know why?
Yes, no.
Yes, because we assume on a layman's language that one bar is equivalent to 1 bar is equivalent to 10 cubic meters of water.
Yes. 1 bar is equivalent to 10 meter cube.
Yes. Or 10 meters of water above sea level.
I'm with you.
In other words, if I want to achieve 1 bar, I pump water from a height of 10 meters. If I want to hit you, if I want water to hit you at 1 bar, I'll climb 10 meters. Anyway, I can see 10 meters height of building. I stay on top of it and I throw water down.
It will fall under gravity?
Under gravity, of course. If you are at the lowest level, that water is hitting you at 1 bar. Let's not digress. Let's go back to where we are. We'll still come to all this. So my screen again. Let me go back to my screen.
Yes.
Good. Yeah. So let's go back to this PowerPoint. Okay, let me send you this PowerPoint now. Just hold on. Let me send you the PowerPoint so you can have it. Have you gotten the other ones?
I've not checked my email.
Okay.
But the content is still there.
Okay, okay. Now what I'll do now is
the PowerPoint presentation is not there.
I'll send you the PowerPoint presentation now.
It's okay.
So that you can follow up with it. And I'm going to be sending you a lot of material. So let me send you a couple of them. But in what I'm sending you now, you see PowerPoint. I'd like you to download it.
It's okay.
I'm supposed to have sent you all these things, but it's okay. Your email again is Olufemi.
Olufede@gmail.com.
OLU.
Yes. OLU. FEDAY.
No, I didn't get it. OLU.
Yes. F as in fish.
Okay.
E as in egg.
Don't worry, I've seen it. I've seen it. Now you might have to check your email.
It's okay.
Well, let me continue. So now, my screen again. So the third thing we talked about now is the expected growth. Are you with me?
Yes.
Under calculation basis, there are 3 things you need to do. After you've done your water demand for different users, whether it's industrial, commercial,
or residential,
production, agriculture. All you need to know is to know the assigned value per person or per unit.
It's okay.
And use it as a basis to build your cost, to build your demand. Now, the next thing you need to do, ask yourself is, what is the growth? Because in water reticulation, you don't design for today. You design for a certain horizon. You design for a certain expected lifespan. You don't say, if you are designing, for instance, you tell yourself, I'm designing this water reticulation for the next 50 years or for the next 30 years. What this means is that after 30 years, nobody should hold you responsible. And in doing that, you must tell yourself, what will be the population of my house in the next 30 years? That is the value you use to design. You don't use the value of today.
But the basis will still remain 100.
The basis will remain 100, but the population equivalent will change. And the safety
for Abuja and Lagos.
No, what I'm saying is, if you are designing for the water we consume will never change.
Yes.
You cannot tell me today you are drinking 10 liters of water, tomorrow you're going to drink 20 liters of water. It's not possible.
But what about if the number of people
that
increase?
Is what you're saying. So that's why we said expected growth. So when we say growth, you should know that we're talking about population growth. So
that will be factored into the design.
God bless you. You must, not will be, must be factored. So what you do now is, like in Abuja, when they designed Abuja, listen to me, they designed Abuja, phase 1 of Abuja, they designed it for 1 million people. But as at 1978, they are now up to 10,000 people in Abuja.
It's okay.
But they said, in 30 years' time, Abuja is going to grow to 1,000 persons. And that is not all. You also use a safety factor to also achieve that. In addition to using your growth formula to achieve that, you have to understand, ask yourself, at what rate is Nigeria growing? At the current, write it down. Nigeria is growing at 4%, urban areas. Between 3 to 4%, that's the growth rate of Nigeria. So you use it. So you go online and check all the population equations, and then you estimate that if 1,000 people are in this vicinity today, in 30 years' time, it's going to be 1,200. You get it?
Yes.
And you also factor in your future development. Future development.
It's okay. Yes. Good. Expected growth and future development.
Yes.
Yes.
I was privy to know about the design of Owerri.
It's okay. Imo State.
Before the war, during the premier of Eastern Region, when they designed Owerri, I believe it's also so in Ibadan or so, one state again in the southwest that was well designed. What they did was, when they are designing, let me demonstrate it through my whiteboard.
It's okay.
You make provision for your end pipes. At your end pipes, you make provision for future development. In other words, let's say, for instance, this is the city as it is now. In the future, there's going to be, let's say, Ogun State. There's going to be Agbara here. There's going to be, I don't know their names, Redeem Camp here. And your water tank is somewhere here. So when you are distributing to the main city, this is the main town that is existing now. You see? You know that there's going to be a future development of Redeem Camp here, but non-existence. And there's going to be Agbara Industrial Park.
Yes.
Here. So you now do, you estimate based on the land use and based on the size of the land. How many people are going to be in this Agbara? Hold on, let me on my annotation. On. Okay. Now, you ask yourself, what is the population of this area in the future? So, assuming this pipe size, we are providing this pipe size. I'm digressing because it's one man training, so I can digress. And here you have 75 pipe size. Because of what you're expecting here, that the pipe size you're expecting here might be 100 because Agbara is going to be industrial area. Yes. You will be forced to go and change this man to 150.
To accommodate.
God bless you. Now you understand what I'm saying.
Mm.
That is future. You must factor in future development.
Mm. Yes.
You must factor in future development.
Right from the onset.
Right. That is what I was trying to refer to you. The Owerri scenario. That was during the British, of course. They did the right thing. So what they did was they know that this city is going to expand in the future. So they use big pipe sizes to start with. You will be thinking they are oversizing or they don't know what they are doing. But no, they are factoring in the downstream districts that are going to come up.
Yes.
So let's go back to this place, the content.
Mm.
The next thing you do, you now estimate the water demand. Now you've done the water demand calculation, isn't it? And you have estimated the population per person per day. By now you've gotten your value, you're going to design it. The next thing you do is now you now design your network. After your network, you do your analysis. After your analysis, you conclude. That's the end of the design.
It's okay.
Any question?
Very interesting. By the time I go through the material send, I should be able to come up with any likely question.
Let me rephrase what we've done in the last 30 minutes. Okay?
Yes.
Somebody comes to you and said, I want to design an estate or a district. The first thing you ask him is, where is the layout? Where is the pipe? Where is the map? What will the map do for you? The map will make you to understand where the houses are. Okay?
The
topography will help you understand where you're going to locate your upper reservoir or your elevated tank.
Terrain.
The terrain. You need to know the terrain. And the major thing you're looking at for is to know the highest and the lowest points. Femi, that's
the landscape.
The landscape, you need to know the highest and the lowest points.
Yes.
What do you need the highest point for?
So that you know how to lay your pipe.
No. The highest point. You are right. You know how to lay your pipe. That's important. But you need the highest point so that you know where to locate your tank.
It's okay.
When I say tank mean reservoir.
I know.
Underground tank, good. It could mean, it's exhaustive. Okay.
Yes. So the tank should be located at the highest point.
Yes, exactly. You know why?
Yes, now.
Gravity.
Gravity, yes.
Then you need to describe the area. The person needs to describe the area. While describing the area for you, what do you look out for?
The area. When we are looking at the area, is for us to know the water source.
God bless you. One.
And to know whether the water is the surface or underground water, and also to get the reservoir, where to locate the reservoir.
Thank you. How about sustainability?
Yes.
In sustainability, what are the three things you want to guide against?
We want to look at the quality and quantity.
And
also the economic of extraction.
Thank you. So then after you've provided those things, either he provide you those things verbally or with documents, okay? In other words, a consultant must have done this, or if you're the consultant, then you are doing your own job, okay? Then the next thing you do is you now ask him, or you look at the map, you now know whether it's for rural areas or urban areas. Is it industry or is it local people? You know why we talk about urban rural areas?
Yes.
For instance, in flushing toilets, you don't tell me you need 8 liters of water to flush toilets. if you're in the rural area. Are you with me?
Yes, I'm with you.
Because they normally use things like pit latrine. Okay.
Yes.
They go to
yes.
farm. They don't take their baths 3 times a day. They don't have cars. They don't wash cars. They don't have gardens. They don't have swimming pools. These are the things you need to factor in. That is why you need to know your water demand
For future development.
No, not future development. Characteristics of your water demand users.
It's okay. It's okay.
It helps
it's okay.
you. It helps you.
The attributes.
The attributes. Then the next one is you need to know the expected growth, isn't it?
Yes.
Why do you need expected
growth? For future development.
Okay. And what is the
for growth?
For growth. Why is it necessary? Because you are designing for the future.
Yes.
Good. Do you know why you need to design all that? Because you don't want to design something today, in 5 years' time, it failed.
And also be changing and be
good. Good. The changes.
At least you cannot be, if pipe is being laid, you cannot be uprooting the pipe and also.
Thank you. That means you need to have the master plan of the area, or at least the right of way.
Yes.
So you don't go and locate your pipe under somebody's building. You know, in Abuja, when Erufai demolished some houses in Abuja, one of the reasons they gave is that some pipelines, people went and built on top of pipelines.
Yes.
You know what happened in Lagos?
Waterways.
You know what happened in Lagos recently? That blast.
Yes, they built on gas pipeline.
Not only here, and they didn't give right of way.
And
let me even tell you what's going to happen in Lagos. When those their rail systems start working, some houses are going to crack.
When the rail system,
Lagos Ibadan Expressway, all the houses that are too close to the railway line,
because of vibration.
God bless you. Yes. So I'm just giving you an idea why you need to factor in these things.
Yes.
Then the next thing now, after knowing your population growth, the future population, and everything, you now use it to compute the water demand. Do you get it?
Yes.
Let me take you back to
using the units.
Using the population, and then using the specific demand, specific value. You know what I mean by specific value?
Yes.
As an engineer, you know, we talk in terms of specific values. Once you know the specific value of something, all you need to do is to multiply by the quantity.
Yes.
You know the flow, you know the demand, okay? If, for instance, I say that one person requires 100 liters of water per day, and you now tell me that there are 1,000 persons, that means I'm designing for. That means the water demand will be what?
Times multiplication.
God bless you. That multiplication. Now, after that, now if you multiply for one house and there are 100 houses, what do you do next?
You multiply by 100.
If it is a district and there are 1 million houses, what do you do?
You multiply by 1 million.
If it is a country, you multiply by the population of the country. So
yes,
it's a straight line thing, isn't it?
That's why we are getting it later per capacity
per second.
Day.
Yeah, per day.
Or second.
Or seconds or hour or minutes.
Yes.
The US will design minute. US will tell you gallon per minute. UK will tell you meter cube per second. SI unit is meter cube per second.
Yes, and we believe that water distribution should
be the lowest
designed based on the simplest unit.
Yes. Which is what? Which is what?
Which is second.
Liters per second.
Yes.
Good. You know what is, pure water bottle, the one we use small, the small one we use. You know, it's 75. It's 750 liter. No, it's 0.75 liters. You are aware?
Yes.
And you know that ever water, the big one. The big one is 1.5 liters.
Which is equal to yes.
Good. So you can imagine. So if you bring 1,000 of it, that will give you 1 cubic meter. This GP tank, the GP tank in your house is either 1.5 or 2 liters. No, 2 milliliter. So the next thing now is you now design your distribution network. Okay. You now design your distribution network. So after that, that will be all.
It's okay.
Good. So now I'm going to give you an example of let me give you, can we have a 5 minutes break? Just 5 minutes. Can you use opportunity to download all the materials I've sent you?
It's okay, no problem. No problem. No problem. 5 minutes break.
5 minutes, yeah.
It's okay, thank you.
All right. I wanted you to not true. You gotta go plenty. Now, we compete everywhere. Everybody will be talk. Everybody will ask
I didn't tell you how to pack it. Okay, I'll show you somebody. One guy.
Okay, you're back.
Yes, fully back.
Okay.
Sorry.
So let me demonstrate something for you now. All this thing we just said now.
It's okay.
Clear all drawings. In your estate, I don't know where you're staying in an estate, yeah?
Yes, I stay within estates.
Okay. Let's do a design for the estate, for instance.
It's okay.
Now, the estate is a built area. So we can use population equivalent. We can count houses, numbers, okay? If it's an unbuilt area, I'll make use of land. In the Nigerian Land Use Act, a particular size of land has a certain number of persons expected to be inside it. Are you with me? If you buy a 1,000 square meter land, it is not possible, it's impossible that 50 people are going to live there.
Yes.
It's impossible unless it's in Manhattan or New York City, where you can build 20-story building. And then maybe 5 people per floor, whatever. I'm just trying to give you an idea. So every location has what they call land use. In Abuja, some areas in Abuja, they will tell you that it is 500 persons per hectare. Are you with me? Some areas, they will tell you 1,000 persons per hectare. So if you tell me that here is 1,000 persons, let me come here. Okay, let's start with unbuilt area. The land use says high density. When you hear high density areas, maybe they are telling you
populated area.
But the technical word is high density area. They will tell you that it's going to be 100. When you hear 100, it means 100 capital. Okay. You don't go and say 100 persons. You sound untechnical. As a water engineer, you must learn how to use the water terminology. That's what sets you apart.
Language.
So, per hectare.
Yes.
I can also say
that unit is per acre. Is more than acre now.
No, yeah, it's more than acre. Yes, 1 hectare is 1,000. 1 hectare is equal to 10,000
acre.
Yes. No.
What about acre? If it is expressed.
1 acre, 1 acre is 2.7 hectare.
It's okay. It's okay. Thank you. Thank you. 2.7. Thank you.
Yeah. So let's call this unbuilt areas. Unbuilt areas. So that means you're talking about empty virgin land.
Yes.
No human beings inside. You can say low density.
Just like for future expansion.
Yes, 400. No, it's like a unit, specific unit of development.
No, I mean on build area.
Okay, yeah. Districts or virgin districts. Medium density.
It's okay. We have medium.
We have ultra high, but let's not go into that. Okay. Yes, very high. I don't know their value. Places like in Lagos, First Stack. Ikoyi.
Yes.
Places like Ikoyi can be over because that's where you see those high-rise structures.
Yes. Ultra.
Good. Now.
Very high.
Yeah, very high. Whatever language you use, you designer can adapt, but it must be reasonable.
It's okay.
Now, assuming let's use your estate now, for instance. Now, it's not a built-up area. So if you want to do design now, the first thing you tell yourself is, what is the water demand per person? So what is the water? Then they have given me the map. They've given me the layout. I can see the number of houses, the street line. I can see the elevation. I can see everything. The next thing is, what is the water demand? Water demand we are assigning per person. And we say let's use what 100 liters per capita
day.
A day.
Liters per capita per day.
The next thing you ask yourself, what type of houses are there? Let's say duplexes, okay? Or let's say block of flats. How many people are in each block of flats? %20. Per flat, per house.
Yes.
Let me use something that is reasonable. Sorry, let me not say block of flat. Let me say a 3-bedroom.
Yes, thank you. Because 3 will be different from 2.
Bungalow. In that case, let's say 10 persons. I know you tell me 6 or 7 or 8, okay? But if we apply a population growth ratio, and let's assume in 30 years time, it's going to be 10 persons per 3-bedroom.
It's going to be
10 persons.
It's okay. Yes.
If you didn't see capita, you can see PE. PE means population equivalent.
Population equivalent.
Now, there's what we call peak factor.
It's okay. Peak factor,
or you call it safety factor.
Is there a template? Is there a template or?
No, I want to show you from first principle.
It's okay.
I want you to grab the first principle.
It's okay. Thank you.
Now, when we say peak factor is just like safety factor, okay?
Mm.
1 × It varies between 1.3 to 2.3.
Range.
Yes. Femi, when you do your design, do you submit your design like that to your clients, or do you multiply by a certain factor of safety?
Yes, it depends on the parameters, factors,
Okay.
the parameters, and also the chart you are using.
Good. Now, in every engineering design, including water, there's always a safety factor. You must apply a safety factor.
Is this constant?
It's not constant. It depends on the number. Is in your material. I'll still come to that.
It's okay.
Now, safety factor. Let me explain to you. This safety factor is what takes care of some unforeseen circumstances, such as leakages, losses, change in design values. You know what we do is safety factor. Sometimes you're not sure of yourself. And when you're not sure of yourself, you just multiply your final value. If a client gives you a bill to do and you got 100 million, you know it's not wise to tell him 100 million. You multiply by 1.1 or 1.2. Okay? And tell him 1 point. Case, for adventure, there are changes in market value. Or there are changes.
Sorry. Have you been to 1004 high rising building?
I've passed it before. Going towards a VI.
Yes.
Good. I passed it. I can visualize it.
You know the layouts of water utility, the water in particular. You know the way it's being laid. There are a lot of problems if there are leakages of waters.
Okay.
To identify. Somebody should be able to calculate, use all these parameters to be able to detect the faults.
Yeah. In the case of 1004, you know it's very high-rise structure.
Yes.
I can bet you that they have their own water.
Yes, they generate their own water. They have their own.
Good. You know why?
They have their own utility.
Thank you. You know why so? Because at that height of building, you cannot use. It is difficult to use a public source.
Yes.
Because where are you going to locate the reservoir, the upper reservoir? Lagos is a flat land. So you find out in their own case, the reservoir is going to be located at the top of the building. I bet you if you go there now, that is where the reservoir is located.
Yes.
Because you cannot do a tank of that height. It's not possible. Even if you do a tank of that height, you might have to exceed the last floor by, say, 3 or 4 meters. So that the person at the last floor can still get water.
Yes.
Then another thing is that there will be some measures to stop excess pressure from affecting the person at the lowest floor.
It's okay.
At the ground floor, sorry. Because I don't know how many floors that building is. Do you have an idea how many floors?
What?
What's the height of 1004?
I cannot say, but you know.
Let's say, okay, let me give an instance.
It's just like an estate.
25 floors. And each floor is about 3 meters.
Yes.
So you're talking about 75 meters high. Did you get it now? At 75 meters high, you're talking about approximately 7.5 bars.
Pressure?
Yes. The pressure difference between the highest point and the lowest, the person is staying at the last floor. The person is staying at the first floor. So I can bet you somewhere at the middle, there must be a water tank somewhere.
Yes.
At the middle. That water tank is to cut off the pressure, because the pressure, if the person at the ground floor is taking water from the topmost tank, it means if he opens his tap, there's a tendency that the rush of water, the pressure of water at his tap will blow the tap.
If they just have a 1 unit tank at the top.
At the topmost. Unless they are going to use some pressure reducing valves.
Yes.
Mm-hmm. So let's go back to where we are now. Now look at our routine. If you are now staying in a 3-bedroom bungalow, and we said that each person in your house, based on national standard, is using 10 liters, 100 liters of water. Okay? And there are 10 people in the house. It means that the water demand of the house is going to be what? 100.
There are 10 people, 100 times 10.
And that would be what?
1,000.
1,000 liters per what?
Capacity.
No more capacity.
It's okay.
Because you multiply by 10. So capacity
it's okay.
Capacity.
It's okay.
So what it means is that if I want to service your 3-bedroom bungalow now, I'll come and provide a 1,000 liters tank for you guys.
Yes.
Per day. It means if I want to be recharging your water every 2 days, how many liters will I provide? How many tanks will I provide?
If
it's every 2 days, I want to be refilling your tank. It means I'll provide 2,000 liters and above. 2,000 and above. Remember, we're talking about minimum value.
Do you have a tank of that capacity?
Yeah, now 2 is simple. Now 2, most of what we have is 1.5 to 2.5. You know, this 1,000 liters is the same thing as 1 meter cube tank per day. So I can try to say per day.
For each unit.
For each unit. For each 3-bedroom of 10 people. For each cube. If I have too much money, I can make it more than this. It's okay. It's nobody's business.
It's okay.
If I want to be supplying water every 3 days, I'll make it 3
times 3.
3, yeah, because I want. It means the return period is what? 3. Means I want to be coming every 3 days. But how about if I want to be recharging your water every 12 hours? It will become 0.5. Every 12 hours. If I want to be pumping water for you every 12 hours.
Yes.
You understand the concept now?
Yes.
Good, okay, let's go back. Now, but I will not say that this value is 10,000 liters. I'll be mistaken. I must be able to multiply this final value by a certain factor.
Safety factor.
Safety factor. In water reticulation, we call it peak value. We don't call it safety factor. In dams, we can call it safety factor. In construction, in building, but in water, you see water, you call it peak factor. Peak demand, peak factor. Once you multiply a value by a peak factor, that value becomes a peak demand. Okay? You must have come across this word, peak and peaking. It's peak. Good. I'm telling you about worst case scenario. Worst case scenario.
Thank you very much. All the best.
Okay, now, you, the designer, you are free to choose between 1.3 to 2.3 what safety factor you want to use. But something must guide you. In the material I sent you, there's a place that will guide you. If you are designing for a small number of persons, you move towards the right. You move towards 2 point something. If you are designing for a large group, you move towards a smaller safety factor. Does it make sense?
Yes.
The reason is that if you are designing for a very large group, we say that variability is low.
Yes, the capacity, the safety
is low. Good.
Because the number of usage.
Yes, is low. The reason is that if I'm designing for a group, large number of persons, I will not worry about too much fluctuation because the fluctuation will be written off somehow. If you are somebody that works with that data, if you're working with the large data, the error will cancel out somehow.
Yes.
But if you're working with a smaller data, the standard deviation will be so high. Good. So now we can say, let's choose a percentage factor of 2 just for ease of calculation. So let's say choose a percentage factor of 2. That means this value becomes 1,000 times 2.
Divide 2.
Does it make sense?
2,000. Yes.
Now let me give you one layman's knowledge. I've done a calculation for your house and I got that 1,000 liters is enough for you guys. But in my wisdom, as an engineer, as an experienced engineer, I provided 2,000 liters. Will you say I'm stupid?
Just to make provision for SS now.
Good. I'm even making provision if in case I could not recharge your water on Tuesday.
Yes, yes. And that's why the safety factor is there.
Good.
Or peak factor now.
Peak factor, yeah.
Or water.
So now it means I need 2,000 liters of water per day. Okay.
For each flat.
Okay.
Per house.
Each per house. Now the next thing is how many houses are in your estate?
Yes.
Let's assume there are 1,000 houses. So the water demand now of the estate becomes 1,000 times what? 2,000. That becomes what?
That becomes
2 million.
2 million
Liters per day.
Yes.
But we said that if you want to convert day
to second.
To seconds.
To allow for water distribution.
Yeah.
Multiply by that.
Yes. Are we good? Are we together?
Yes, we are. Very much.
These 2,000 liters, let me start here. It means these 2,000 liters now, I'm going to divide it by what?
24.
No, just say A6400 instead of doing those.
Yes, yes.
Time. Now, we want to convert it to meter cube per seconds or liters per seconds.
Meter cube per second. You divide by 1,000.
No, I'm not divided yet. So that would be 2 million.
Okay.
Divided by what? A6400.
1,000 to meter cube.
Okay. I get you, brother. You are following. You are really following. You are really following. Huh? Then multiply by. I hope you not get confused.
No. This one is a familiar terrain.
Okay. Does it make sense?
Yes, very, very well. So you are changing it to seconds now instead of day.
Yes.
Converting at the same time to second.
I'm converting two parameters at the same time.
Yes. Yes. To meter, it will now be meter per seconds. Meter cube per seconds.
Good. So the value now, I'm using my calculator now to calculate it.
Yes.
2 million divided by 1,000. Then divide by
86,400.
86,400. It's giving me 0.023.
Meter cube per second.
No.
Hmm?
Yeah. Meter cube per seconds.
Second.
Or if I want to leave it at
Liter per
liter per seconds, that means I'll multiply again by 1,000.
Yes.
That will give me 23.1. Or let's say 23, okay? Let's forget about this.
230.
No, it's 23.
It's okay, 23. Sorry, 23 per seconds.
Do you know what this means?
Mm.
What it means is that in your estate, in your house, in your house now, if I want water to be consistent, I need about 0.023 liters. Remember that this 23 liters is for 1,000 houses.
Yes.
So it means this is the quantity of water that must be flowing every seconds in that estate. So this is now the water demand that must come into that estate per seconds.
Yes.
You get it?
That's why we said that water distribution should be expressed in the simplest unit.
Thank you.
Because water must be available
around the clock.
All the time.
Good. So my job now is this 23 liters per second. I'm going to ask myself a question, and that will be the end of your design. What pipe size can deliver this? What size of pipe can deliver this? If you use a very small pipe, it will not flow.
Yes.
It will not deliver this quantity per second. If you use a very big pipe, it's waste of money and it will resist the pressure.
Yes.
So it means this is where the designer, this is now, you know, before we arrive at this, we have to pass through a lot of things. You have to determine the number of houses. You need to determine how much water each person will take. Are there hotels? Are there schools? If there are schools, there are hotels. You will not just say 1,000 times 10, then times 1,000. It's not possible. You will start to talk about the school, you know, the population of the school, the water they need, hotels, recreation areas, industries. By the time you finish all these things, you know that you're going to do a lot of work. You get it?
Like in my area, as a chemical engineer.
Okay.
Hello?
I can hear
as
you.
a chemical engineer, you will deal with fluid mechanics.
Yeah.
When we talk about PMS,
Yeah.
so you know, or gas, you know that there are some deposition on it.
Okay. Okay.
Deposition on it.
Okay.
And at the same time, that will be also made provision for in future.
Okay.
Because as the fluid passing through the pipe,
yeah,
there may be some deposition.
Okay.
Around the pipe.
But the safety factor, will safety factor take care of it?
It's okay, safety factor is okay.
Okay.
It's okay because we are just looking. I just want to see how this can be applicable to to PMS or crude oil.
It can.
And likewise, water also has some impurities and thereby that can also even corrosion.
Yes. And that's why you need to size the pipe very well.
Yes. And I think with the peak factor, that will be because we just need what we need per house is 1,000 liters per day.
Okay, sir. Yes.
And with the peak factor, we've been able to get 2,000 liters per day.
Yes.
So all those things will have been factored in.
Yes. So I'm happy you are following and you're getting it.
Yes.
Yes, maybe because
That's why the peak factor is very necessary.
it's very necessary, my brother. Now, with this 223 now, the next thing you do is you go and ask yourself, what pipe size can convey this material? Now, for you to get the pipe size, for you to get any pipe size, there are 3 parameters you need to look out for. The first parameter is called frictional factor.
Is okay. Frictional factor.
Roughness.
Is okay.
Frictional factor of the pipe or roughness of the pipe.
Yes. I think this, as we also cover for corrosion.
Thank you. See, this is about fluid. Fluid is fluid. Whether fluid mechanics or hydraulics is the same thing.
Yes.
Number 2, you ask yourself, what is the slope of the pipe?
Is okay.
Are you there?
Yes, I'm with you.
Number 3, what is the flow, expected flow in the pipe? Or
okay.
The Q, or the demand?
The Q should be the flow rate.
The same thing, yes.
Yes. Or what? The demand.
The demand. Or some people can say, what is the discharge? All these things mean the same thing.
It's okay. It's okay, yes.
And you know that discharge is equal to AV.
Yes. Yes.
Or AIC. You did hydraulics. You should have something this. Where C
is there. Q, the flow rate. Is the coefficient.
Coefficient, or what again can we call it?
Or thermal is no.
No, you're right. You're right. Say it. Whatever you call it, safety factor, whatever.
Yes, safety factor. Yes.
That coefficient can be the orifice, this type of orifice. It could be the friction of the bottom. It could be the friction of the pipe. It could be anything. It just means the same thing. You know, engineering is unique. Engineering is a natural science. How do I put it?
Yes.
It's mathematics. Sorry. So now, you can start to use formulas now. V, we know what A is. A is now the surface area of the pipe. Is the diameter of the pipe you're looking for.
Which is meter square times meter cube.
Thank you.
No. V is what?
Meter square times meter per seconds.
V is what?
Velocity.
It's okay. Sorry, I thought it's volume. It's okay.
No, it cannot be volume again. You know why?
It's okay. No,
you have a point. It could be volume, but it will not be volume per second.
It's the flow rate.
Flow rate. And that flow rate cannot be in cubic meter per seconds.
Yes. It
has to be in meter per seconds.
That's the flow rate. I mean volume, velocity. So this one will be meter cube per second.
Meter cube per second. You mean the big Q? The big Q.
Yes.
Good. Now we have the big Q. We're looking for the A. You know the V. We don't know the V. Because if we have the V now, we're looking for A, remember? So if you have Q, you have the V, you just say Q over V equal to A, isn't it?
Mm.
But you don't have the value of V. In that case, you are not going to use a chart to do it.
It's okay.
You use a chart we call, there are many charts in the markets, just like in engineering, we have many charts. I know in chemical engineering, you guys have many charts as well.
Mm.
But there's a chart we call nomogram.
Mm.
That chart is in the last email I sent you.
It's okay.
Open it. There are 3 charts. Nomogram. It's called nomogram.
It's okay.
It comes in 0.1, 0.4, and 1.
To get
Now,
the value of
to get the size of pipe,
velocity.
the diameter of pipe, diameter now.
It's okay.
Do you understand this formula?
Yes, now.
Pi.
You are looking at the area now.
Yes, thank you.
The radius.
Thank you.
Hmm? Hello?
I'm with you, sir. Yes.
I said you are looking at the radius.
Yes.
Pipe. Yes, the radius, yes. Yes.
No.
Yes.
Do you get it?
Yes, now R. You represent it by R.
Can you go to your chart?
Mm.
There's a chart I sent you called nomogram. Let's say we are using a PVC pipe. I'll open it. PVC pipe, eh?
Mm.
See, Femi, the smoother
Yes.
the surface is, the less friction, true or false?
Yes, true.
So if you see all these PVC pipe, especially these white ones, their frictional factor is very low. So 0.1, can you write? 0.1 is for PVC.
0.1
is for PVC.
is okay.
0.4 is for iron, ductile steel.
It's okay. 0.4 iron.
Yeah, ductile steel. Ductile steel. The 1.0 is concrete.
For concrete is what?
0.1. No, 1.0, sorry.
1.0.
It's all written there.
It's okay.
Okay. So let's continue. So now I want you to open that chart, if you can.
I may leave the. If I should open the chart, I will leave the.
Well, it's important you leave it because if we want to generate this A through calculation,
it's okay.
It will take us time.
It's okay. And let me.
Solution. You know, profit.
Can you see my screen?
Yes. We'll go there.
Can you open this?
Yes, I want to download the.
I
Yes,
can give you 2 minutes. Go ahead.
it's okay.
Just shut me up. You finish.
Yeah, what did you do it? Okay. Yeah.
Oh, sorry. Oh.
You there?
Yes, yes.
Have you opened this?
Let us go on, sir.
Okay, I see my own now. This is 0.1.
It's okay.
Now, this is a chart. Later, if you find time, is it possible for you to print it? Maybe after tomorrow.
I will print on my end.
Yeah, can you print on your end maybe by tomorrow so that I can use it and teach and show you and demonstrate
Yes,
very
yes. Yes.
well? Because the demonstration will not really. That might be one of the limitations of this Zoom. Okay.
Maybe tomorrow.
Okay, tomorrow. Good. Now, please try because this is the cocoa. You see this chart, You know, in engineering, most designs is chart and table. Chart and table will save you the energy of doing long mathematical calculation. Now, look at this now.
It's okay.
On the vertical is a slope. This is the slope of the land, which automatically means the slope at which you're going to lay the pipe. On the horizontal is the flow. So, in other words, then on the diagonal is the pipe sizes. Is the pipe sizes. Then on the opposite diagonal is the velocity at that point. So in other words, you are going to impute 2 parameters and get 2 parameters outside. One of the most difficult things to calculate is the velocity at which the water is running. Because if I can get the velocity,
yes,
it's easy for me to get the A. But the velocity is an instantaneous thing. You can't get it. It's not possible.
Yes.
So that means you need to use reverse engineering to get it. So that means if you get the slope, in fact, not 3 parameters. Because if you look under, I'm trying to see annotation. Spotlight, sorry. This is what I've been looking for. It's not showing. If you look here now, you see you see my cursor?
On the whiteboard?
Not on the white. Okay, is it showing? No, on my chart.
It's okay. It's okay.
Okay, I can see. It's only on the whiteboard it wants to show.
No. I can equally see on the.
Okay. Now, if you look at this chart, it's telling me that I'm using a PVC pipe. By the K factor is 0.1. It means that the friction between the water layer and the pipe material is very slow. It means the water losses is very low. The rougher, the higher the K factor. So now, the next thing I need is to say, what is the slope? What is the what? Slope. And the slope here is talking about what is the slope of the land. So you need to establish a slope. And what is the slope? Slope is the difference between the vertical over horizontal. Let me demonstrate it. Let me demonstrate slope for you on the whiteboard. On the whiteboard. Eh? Slope. Oh my goodness. Is just hold on. Let me remove. Is it remote control? No. Whiteboard. New share. Okay. I'm trying to show you, remind you, so not really show you. Okay. Whiteboard. Come on the whiteboard. Slope means slope means vertical over horizontal.
Yes.
So it means if I know the point A and point B, their height difference over the horizontal distance will give me the slope. Shikena. Point A is 90 meters and point B is 92 meters. And the difference between the 2 points is 10 meters. It means the slope is 92 minus 90 over 10. It means it's 2 over 10. I need to demonstrate this thing for you, but I bet you understand it.
Yes, I will guess. I will try to get it. Just let us continue.
Okay. So here, slope equals vertical over
Yes, now the increase in y all over increase in x.
God bless you. So if I have something like this,
y there, the increase in y. At least let the y be be vertical be y axis and x, and horizontal x axis, which is the same thing as gradient.
Yes. This is vertical.
That's y axis. And the horizontal Yes, I get the concept. Hello?
I can hear you, sir.
I can get the concept. That's angle of inclination.
Yeah.
I can get the concept.
Okay. So we can continue, eh?
Yes, we can continue.
Now. So looking at this chart, now, let us assume a slope. So this slope now that we got now, 92 minus 90 over 10, that is 1 over 5. 1 over 5 means 0.2. So the slope is 0.2, isn't it? So you come here, 0.2 in our terms we mean 2. 0.2 means what? 2. Why? Because this chart is per mil.
It's okay.
Per mil means is over 1,000. Look at the symbol here. Can you see my hand? Mouse. So 0.2 becomes 2. So the discharge you had then was 23. So I'll come here and choose 23. I'll come here and choose 23 and measure it up. I see my hand against 2. You see where it's ending? It's landing between 200 mm and 250. 250. It's landing between 2 pipe sizes. If you can't see it, let me know.
I can't see your hand, but I'm following you.
Okay. You can see
your camera, your video is blocked.
It's blood.
Yes.
It could be network. But what I'm telling you now, that 23 liter we got now, I will mark it up to the slope of 2.0. So as slope on 2.0 now, I will say, where does it fall? So if you're looking at it, you see that it's falling between 2 pipes. Pipe 200 and pipe 250. Can you see it? Then I want you to look at the other angle too. It's also falling between 2 lines that is going downwards. And those 2 lines are V 0.7 and V 0.6. Can you confirm that, please?
It seems you didn't put on your video.
Oh.
Yes.
Your
video is, yes, you just put it on.
Now, are you seeing my screen?
Yes, I can see your screen very well now.
So all this while you have not been seeing my screen?
Yes. You
would have told me now.
But I'm I felt maybe you are doing something.
No. Can you see where I am?
Yes, I can see you very well.
Where I am? Where am I?
Let me.
I'm between which numbers?
You are at the back of the banana.
No. I mean my cursor. Where is my cursor?
On the whiteboard.
No, not on the whiteboard. On my screen.
On your. Let me.
I'm not sharing my chat with you. Now
yes, I can see. Good. Yes.
Where is my?
Yes, I can see it.
Where is my cursor now?
Yes, I can see it now. I can see it now.
Follow. Okay. Do you see where the mouse?
I can see the chart.
Do you see where my mouse is?
On the chart?
Yes.
No, I can't locate your mouse.
My mouse is on the horizontal.
Yes, I can see it. I can see it now.
So
at the base.
I'll take my mouse. 20, these are 23. 23
yes, you are moving 2. It up.
23 against 2. So it's falling between 2 lines.
2 lines.
Those 2 lines are 200 and 250.
It's okay because it's between 10 and 20.
No, between 20. No, I'm at 23. I just went to 23.
Your mouse is at above 20 now.
Oh, that's not 20. Sorry, that's 2.0, sir.
Is that yes, 2.0.
2.0. That's the slope. Slope in per thousand. Okay. Slope in per thousand.
It's okay. Where can I know you've sent the chart to me, but where can one download the chart or get the chart? Is there any handbook?
No, actually, they give us this chart. There are many charts in the market. Some companies have developed their own charts.
It's okay. What are the variables?
The variables you need in the chart is the slope of the land, your discharge, and the K factor.
K factor.
K frictional factor. The roughness of the pipe.
It's okay.
The roughness factor. The roughness factor of the pipe is called K factor. K stands for friction.
It's okay. It's okay.
One. Okay, now do you see where I am now?
On the chart?
On the chart.
Yes.
I'm between 300, 200, and 250.
Yes.
Now, if you go down, I'm trying to put a marker. Let me see if I can take a marker.
Yes, now. The marker light blue.
Here.
Yes.
See
Yes.
where I am.
Yes, I can see. Yes.
Now, it's between pipe 200 and pipe 250. Then on this side is between this line and this line. And this line, if I go down on this line.
The chart is not so difficult for me to comprehend.
Okay.
Because we use the same chart, psychometric chart.
Okay.
Just similar like this.
Okay.
Psychometric chart.
Okay. I don't know of it.
To calculate humidity.
Okay.
Percentage, saturated, all those things.
Okay.
It just look like this.
Okay.
And this is the way we take the reading.
Okay, good. Oh, wonderful. So you can see that the chart is pointing at 0.6. Then the other upper one, this other one, is pointing at 0.7. So it means the velocity, see, in engineering, there's no, engineering is a science of approximation. No exactness. You can't just say the velocity in this pipe is 6. No, it will be between 6 and something. So the velocity here is between 0.6 and 0.7, which is okay, because the minimum velocity we need in the pipe is less than, it must not be less than 0.3. You can write it down.
It must not be less than
0.3 meter per second.
0.3 meter per second.
Yes, and the maximum is 3 meter per second.
Maximum.
Yeah.
3 meter per second.
Yes. Did you get it?
Yes, I have it. I have it with me.
Now, for this side now, you can see that the pipe, where's my notation again? The pipe is between pipe, between pipe 200 and 250. Can you see it?
Yes.
So it means in engineering, when you have such thing and it's at the center, you are trying to choose the bigger one.
Yes.
So that means the pipe we need to convey these 23 liters of water is 250 mm. And that is the design. That becomes the design. Did you get it?
Yes.
Good. That becomes the design. Any question?
I think with the materials sent to me, I just need to study them. Maybe by tomorrow, if it...
see what you can do for me, yeah?
Yes.
Normally this class lasts for 2 days, 3 days. Because of the online, I put it 3 days, but because it's only you, I will aim to crash it 2 days.
It's okay.
I aim to, because you are following very perfectly. Imagine if we are 20 persons. You know that some people will be drawing us back.
Yes.
So that was why I put that extra 1 day.
It's okay.
So, but you have a lot of work to do. Those materials I sent you, I want you to go and read them up.
Yes.
The good thing is that you're already a chemical engineer.
Yes.
It's not going to be difficult for you, but if you do it, by tomorrow, you will flow very well. But before we call it a day, I'll have assignments you have to do here and pass here now. So carry your pen. Let me show you.
It's okay.
Now, open.
No.
Sorry?
Yeah, I'm listening to you.
Okay. Now, that PowerPoint, have you opened your PowerPoint? The one I sent you.
I will. I will open it. I have not opened it.
Please open it now. It's important because I want to give you one small exercise to do
It's okay.
to consolidate what you have learned today.
It's okay. Sorry.
Okay.
Let me open it.
Good. This is the assignment.
It's okay.
If you don't have it, you can use my screen, but it's good that you open it.
Is it on the second material or the first?
On the second email.
It's okay.
The one that has the monograph and the rest of it.
It's okay. It's okay.
Mm.
I've downloaded it, but I'm trying to. Yes, I've seen the PowerPoint design for design case.
Yes, thank you. Open it. Then go down until you get to this point.
Sorry, it's coming up. Sorry.
No problem.
Yes, I can. I'm there.
Now,
I'm there.
This is a layout of a city.
Yes, in the introduction.
No, after the introduction, go down.
It's okay.
Go
Objective.
to page. Go down.
It's okay. Study area.
Go down. Go to page. I don't know the page I am.
It's okay. I've seen it.
Here.
After the study area.
No, go down to look at my screen. Are you seeing my screen?
On your screen, I think what we still have there is the chart.
Okay, it must have changed by now. Can you see it now? Can you see my screen?
No. I'm coming. I'm coming, please. Sorry.
No
No.
Can you see?
Yes.
Can you see the layout?
Yes, I can see the layout.
Good. This is
I can see the layout.
Now, if you are designing for a city, you must not have one tank. It mustn't be one tank.
240.
The whole city. This is a city that has 4 different tanks.
Commercial, housing.
East, commercial south, housing Foche, industrial north, swimming pool, center, and the rest of it. So now what I want you to do is very simple.
Yes.
If you have tanks like this, in water reticulation, there's what we call primary pipe. Primary.
Yes.
Secondary.
Yes.
We have tertiary.
We have tertiary.
Tertiary, yes.
Yes, yes.
Primary pipe or main pipe is the one coming directly from the tank.
Yes.
And it's the most important one. If you got it wrong, others will run. So we're going to design, that's the most water reticulation. What they design is the primary. Once they design the primary, when development comes, you can design the secondary.
They factor in others.
In fact, thank you, because the head is already correct.
Yes.
In Abuja, our main pipe, our main primary pipe in Abuja is 1.5 meter diameter. Did you get me?
Yes.
1.5 in Lagos. There's one tank I used to know. If you're going somewhere in Lagos that is even exposed, it's about 1.2 meters. One big tank, one big pipe. So once you design that one and get it right.
Sorry, my data is almost
okay. So what you do is the assignment, convert this into liters per seconds and convert this. This is the water demand, just like we did today.
Yes.
Like commercial east, their water demand is 706 meter cube per day.
Yes.
I want you to convert it to liters per seconds.
It's okay. It's
Using a
okay.
safety factor of 2.0.
2.0.
Yes, and
Yes.
using a K factor, K value of 0.1, frictional factor of 0.1. Using a slope of 0.25.
2.2.
0.25.
Is okay. K factor of what?
K factor of 0.1. That means use PVC pipe.
It's okay. 0.1.
So I want you to get me the pipe sizes. These red pipes. What are their sizes?
It's okay. Pipe sizes.
Yeah, their pipe sizes.
It's okay.
So you do it tomorrow. Then try and read all those materials so that you come to the same.
Yes, I will do.
With
God helping me. I'm highly grateful. Thank you very much.
It's okay.
It's a very interesting lecture.
Okay.
And well delivered and very, very explicit.
Thank you very much.
I'm grateful.
Teaching is my passion.
Yes. Thank you.
So we'll see tomorrow, same time.
God willing.
And we'll do computer application.
Okay.
Before then, I'll send you email so that you can download the software ahead of time.
It's okay, sir. It's okay.
EPA.gov.
Yes, it's okay.
Google it, you see it. Free source, open source.
It's okay.
All right.
It's okay, sir. Thank you. I'm highly grateful.
All the best.
It's the same.
All right.
Enjoy your day, the remaining of your day. Thank you.
Yeah, bye.
Thank you.
Yeah.
Thank you.